Today we are going to prove by infinite descent that the cube root of 2 is irrational. Before we do this, we're going to have a look at the proof by infinite descent of the irrationality of the square root of 2, and we note that by the well-ordering principle, any set of integers must have a smallest element. If the square root of 2 is a member of the rational numbers, then root 2 equals p upon q, where the greatest common divisor of p and q equals 1, so this q must be the smallest of all the integers, such that when it's multiplied by root 2, you get a natural number. We now note that 1 is less than root 2, which is less than 2. We take 1 off each side of the inequality, and we discover that 0 is less than root 2 minus 1, which is less than 1. So that if I take my inequality and I multiply all sides of it by q, I find that q multiplied by root 2 minus 1 is less than q. But q times root 2 is an integer, and q is an integer. So if we look at what's going on the left-hand side there, so that on the left-hand side I have got q times root 2 minus 1. But this, on the left-hand side, is an integer, which when multiplied by root 2, gets me an integer, and it's smaller than q, which contradicts my assumption that q was the smallest number by which you could multiply root 2 to get an integer. And so we can see, if we multiply the left-hand side of this inequality here by the square root of 2, we get q times 2 minus root 2, which is 2q minus root 2q, which is an integer minus another integer. But q times root 2 minus 1 is smaller than q. And so I have found an integer smaller than the smallest one, which when multiplied by root 2 gets you an integer. And so by the well-ordering principle, the square root of 2 is irrational. We now consider the cube root of 2. 1 is less than the cube root of 2, which is less than 2. I now take 1 off each side of this inequality, and I obtain 0 is less than 2 to the power of a third minus 1, which is less than 1. And if I assume once again that q is the smallest integer, with the required property, I find that I can't apply the proof in the same straightforward way as before. It is indeed true that q times cube root of 2 minus 1 is less than q, but if I multiply this on the left-hand side by 2 to the power of a third, I obtain this. Now this here, q times 2 to the power of a third, is an integer, but this may not be. And so I can't at the moment use the proof as I did before, so I have to think of something different. So I consider the case of 2 to the power of 2/3, which will be p squared over q squared, where the greatest common divisor of p squared and q squared is 1. So that q squared will be the least integer, such that q squared minus 2 to the power of 2/3 is an integer, and when it's multiplied by 2 to the power of 1/3, it will be an integer. So q squared has the property that it's the smallest integer when multiplied by 2 to the power of 2/3 and 2 to the power of 1/3, you get an integer. So that q squared is the smallest integer such that q squared times 2 to the power of 1/3 is an integer, and 2 squared times 2 to the power of 2/3 is an integer. And so if I look once again at my inequality here, the element on the left hand side, I have now discovered that q squared cannot be the smallest integer with this property, and yet there must be an integer with this property if the cube root of 2 is to be irrational. And so I have now completed my proof by infinite descent of the irrationality of the cube root of 2.